Welcome to Everyday Explained, your daily 20-minute dive into the fascinating hows and whys of the world around you. I'm your host, Chris, and I'm excited to help you discover something new. Let's get started.
Okay, let's jump into this. Think about your day. How many elevator rides? Maybe more than you even realize.
Easily. You step in, push a button, doors close, doors open, done.
Right. But get this, the national elevator industry says U.S. elevators make something like 18 billion trips a year. Billion.
Whoa. That's hard to even picture.
Exactly. They're everywhere, totally essential for, how we build things now. But we barely think about them.
It's true. It's like this invisible workhorse. You interact with it constantly, but you don't really see the engineering behind it. Feels almost like magic.
Totally. Walk in a box, end up somewhere else, poof.
But behind that feeling, there's just this incredible mix of physics, clever mechanics, safety engineering, refined over, 150 years?
Absolutely, and that's what we're doing in this deep dive. We're going to use these sources we've gathered to, pull back the curtain a bit.
Yeah, look under the hood.
How do they actually move? What's this crucial part we never see? How are they kept so safe? We'll look at different types, why they're used, how tech's still changing things. You've ridden tons of elevators, right? But let's figure out what's really going on when you travel between floors. You might look at that next ride a little differently.
Oh, I think you definitely will. The basics seem simple, sure, but when you understand the why, like the counterweight or the sheer number of backup safety systems,
Yeah.
it really clicks.
Okay, so let's start right there, the basics. What's actually making that car go up and down?
Okay, so at its most fundamental level, you've got the car. That's the box you ride in.
Right.
Then there's the power source, usually an electric motor. And then the system connecting them, cables, maybe belts, and pulleys.
So the motor's job is?
The motor, typically up in a machine room, provides the turning force. It rotates a big grooved wheel called a sheave. S-H-E-A-V-E.
Ah, sheave. Okay, and the cables run over that.
Exactly. The cables, or sometimes special belts now, are attached to the car, loop over the sheave, and, well, we'll get to the other end in a second. The motor turns the sheave, the cables move, the car moves.
Simple enough.
Well, mostly. The motor often uses gears, too. That helps control the speed smoothly, so you get that gentle start and stop, not a sudden jerk.
Right, you definitely notice when it's not smooth. And speed's a big factor, yeah. Residential lifts feel way slower than office tower ones.
Oh, huge difference. It's all about design and capacity.
Ah.
High-rises need speed, lots of people, long distances. A small apartment building, slower is fine, less demand.
Okay, motor, sheave, cables, car moves. Seems straightforward. But you mentioned something else. There's this really clever part that makes it all work better, right? The counterweight.
Ah, yes, the counterweight. Absolutely the unsung hero of the typical traction elevators. Basically a big, heavy block, steel, concrete, whatever.
Okay, where is it?
It's in the shaft, too, connected to the other end of those same cables that lift the car. And here's the key thing. It moves in the opposite direction to the car.
So car goes up, counterweight goes down.
Exactly. And it's heavy. It's weighted to be about the same as the car, plus roughly half the weight of the passengers it's designed to carry.
Half the passengers. Why half?
Think of it like balancing a seesaw. If it balanced the empty car exactly, the motor would have to lift all the passengers. If it balanced a full car, the motor would struggle to lift an empty one. Balancing the car plus half the load minimizes the maximum difference the motor ever has to handle, whether going up or down, full or empty.
Ah, okay, that makes sense. It minimizes the effort needed.
Precisely. It dramatically cuts down the work the motor has to do. Instead of hoisting the full weight of a loaded car, the motor just needs enough power to overcome the difference in weight between the car side and the counterweight side.
That must make a huge difference in how much energy it uses.
A colossal difference. That's a key point in the sources. Without it, you'd need a much, much bigger motor, like a simple crane. With it, you just nudge the balance. The sources mentioned typical motor power is maybe 5 to 15 kilowatts. That efficiency, it's largely down to the counterweight.
Wow. Serious energy savings built right in. And I think you mentioned it helps the cables too.
Yeah, less net load means less strain on the cables, makes them last longer, adds a safety margin. And it makes braking easier, too. The brakes aren't fighting the full weight of the car, just the imbalance.
It's really quite elegant. I saw a mention of duplex counterweightless elevators. Is that different?
That's an interesting variation, yeah. Instead of one car and one counterweight, you have two cars in connected shafts. They move opposite each other, so car A going up helps balance car B going down.
So they act as each other's counterweight?
Essentially, yes. Another way to get that balancing effect without needing a separate deadweight. Clever stuff.
Really is. Okay, so that counterweight system is key for traction elevators, the kind we see in tall buildings. But not all elevators are like that, right? Different buildings, different tech.
Absolutely. You use the right tool for the job. Traction is great for height and speed, but other systems are better suited for other situations. The sources cover a few main types.
Like hydraulic elevators, you see those in like 3 or 4-story buildings a lot.
Right. Hydraulic systems use fluid pressure. There's a motor, but instead of turning a sheave, it powers a pump.
A pump?
Yeah, a pump pushes hydraulic oil into a cylinder.
Yeah.
Inside the cylinder is a ram, basically a big piston. That piston pushes the car up.
So it's pushed up from below? Or the side?
It can be either. Direct acting systems have the ram right underneath the car. Indirect acting systems might have the ram off to the side, connected to the car via ropes and pulleys, strangely enough.
And they're mostly for lower buildings.
Generally, yes. They don't usually have the speed or the height capability of traction systems,
Hmm.
but for low-rise, they have advantages. Simpler design sometimes, easier installation maybe, can mean a smaller machine room.
But energy-wise, you mentioned the counterweight saves energy for traction. Do hydraulics have that?
Typically, no. That's a key drawback mentioned in the sources. Most traditional hydraulic designs don't use a counterweight. So the pump has to do all the work of lifting the car and its load against gravity. That usually means higher energy consumption compared to a balanced traction system, though some newer hydraulic designs do incorporate counterweights, trying to get some of that efficiency back.
Interesting trade-offs. Okay, simpler maybe, but potentially uses more power. What about pneumatic elevators?
Yeah.
Using air. That sounds futuristic.
It does, yeah. Pneumatic elevators are pretty neat, often used in homes. They work by air pressure differences. Imagine the car inside a sealed vertical tube.
Mm.
A system at the top, usually vacuum pumps, removes air from above the car. The normal air pressure below the car then pushes it up into that low-pressure area.
So you're lifted by a vacuum.
Kinda, yeah. Lowering is just letting air back in carefully. The sources point out they're quiet, pretty energy efficient, and don't need all the mechanical bits like cables or hydraulic rams. Plus, they often have those cool, round glass designs, panoramic views from your home lift.
That would be quite an experience. Okay, one more type mention. Screw-driven lifts.
Right, another one often found in residential settings. These use, well, a big screw. There's a long threaded steel column, the screw, running up the shaft. A motor, often attached to the car itself, turns a drive nut that moves along this screw.
So the car literally climbs up the screw thread.
That's the idea.
Yeah.
Motor turns the nut climbs the screw, the car goes up. Or reverses to go down. The big advantages highlighted are that they're very space efficient, no machine room needed, no pit below usually, no counterweight space, very quiet too, and often easier to install in an existing home.
Amazing how many ways there are to solve the same problem, moving people vertically. But, okay, with any of these systems, lifting people hundreds of feet, safety has to be absolutely number one.
It is the paramount consideration. And you can't talk about elevator safety without mentioning Elisha Graves Otis. Back in the mid-1800s, lifts or hoists were dangerous if the rope broke. Well, that was it.
Gravity wins.
Right. But Otis, in 1861, technically, though he demoed it earlier, invented the safety elevator.
Yeah.
Not just a lift, a safe lift. His invention is genuinely what allowed architects to start thinking vertically,
Yeah.
building skyscrapers.
His demo at the Crystal Palace Expo, cutting the rope, legendary stuff. But how did that first safety brake actually work? What was the mechanism?
It was brilliantly simple, according to the sources. His elevator car ran between vertical guide rails. These rails had teeth, like a ratchet. On the top of the car, he had these spring-loaded hooks, or pawls.
Okay.
Normally, the tension from the lifting rope held these pawls away from the teeth, pulled them in. But if that rope went slack, if it broke, the spring would instantly snap the pawls outward.
And they'd bite into the teeth on the rails.
Exactly, jammed right into them, stopping the car almost immediately. It was a purely mechanical backup. Fail-safe. Genius for its time.
A total game changer. And obviously, modern elevators have built massively on that concept. Multiple safety layers now.
Oh, absolutely. Today's elevators have layer upon layer of redundancy. It's far beyond just that one mechanical catch.
Like the brakes themselves are more advanced.
Yes, modern safety brakes are heavy-duty systems. They engage not just on cable failure, but for other issues too, power loss, sudden stops, going too fast. And they usually work by clamping down hard on the actual guide rails, bringing the car to a smooth, controlled stop.
And there's something to stop it going too fast in the first place.
That's the overspeed governor. It's a separate system, Could be mechanical, could be electromechanical. It constantly watches the elevator speed.
Like a little speedometer?
Sort of, yeah.
Yeah.
If the car exceeds a preset safe speed, the governor trips. It usually has these weights that fly outwards with centrifugal force. That trip then activates the main safety brakes we just talked about. Stop the car now.
Vital backup. And the cables? You don't just rely on one, right?
Definitely not. Elevators use multiple steel cables, each made of many strands of wire. Each individual cable is strong enough to hold the car on its own, usually several times over. They have huge safety factors,
So if one somehow failed,
which is incredibly rare given inspections, the others would easily hold the load. The sources mention that Chicago incident at the former John Hancock Center. One cable broke, apparently made a loud noise, scared people badly, but the other 6 cables held. The safety systems worked, car descended slowly, everyone was rescued safely. A real-world test, unfortunately, but it proved the redundancy works.
that's incredibly reassuring. What about the doors? People worry about getting caught?
Door safety is huge. You've seen those light beams, right?
Yeah.
That's often a light curtain, multiple beams creating a safety net. If anything breaks those beams, a hand, a bag, anything, the doors won't close or they'll reopen. Plus, they're physical sensors, too.
Yeah.
And crucially, door interlocks. These are electromechanical locks that ensure the car absolutely cannot move unless all doors are fully closed and locked. Prevents people falling into the shaft.
Okay, that's a lot already. Any other safety layers?
Yeah, the sources list quite a few more. Overload sensors. The elevator won't move if it's too heavy. That's
Okay.
why you see those capacity signs.
Right. Weight limits?
Emergency stop button inside the car. Emergency communication, a phone or intercom to call for help. Some home lifts have automatic shutoffs and power outages. Child locks even. Depending on the type, things like special valves for hydraulics, chain protection, and way down at the bottom of the shaft,
What's down there?
buffers, big springs, or hydraulic shock absorbers. They're the absolute last resort. If somehow everything else failed and the car descended too fast, the buffers are there to cushion the impact.
Wow, safety net after safety net after safety net.
Yeah.
And for fires?
Yes, firefighter service, a critical feature. It's a special mode, usually activated by a key switch, that lets firefighters take direct control of the elevator, bypassing all normal calls. Essential for them to move gear or rescue people safely during a fire.
Okay, with all that built in, it really does make you feel secure. The sources do mention potential hazards, though.
They do, but it's crucial context. They list things like entrapment, getting stuck, often door-related, overloading, brake issues, electrical faults, structural problems, power failures during storms, even human error like sticking a hand out. These are potential risks.
But the whole point of the systems we just covered is to prevent those, or handle them if they happen.
Exactly. That's why the sources stress that elevators are statistically incredibly safe because of all those systems and because of required maintenance. The hazards exist in theory, but the engineering is designed to make failures that cause injury extremely rare, provided the elevator is properly maintained.
Which brings us neatly to maintenance and rules. All this tech is great, but only if it's kept working.
Absolutely fundamental. Regular professional maintenance is not optional, it's essential. The sources generally suggest maintenance checks by qualified technicians every 6 months or so, and then formal inspections, often yearly, usually mandated by law.
What do they actually check during maintenance?
It's pretty thorough. Cables, pulleys, brakes, obviously critical. The control system, the brain, the motor itself, the car structure, counterweight, guide rails, doors and all their safety sensors and interlocks, electrical wiring, lubrication, replacing parts that show wear. And, crucially, testing those safety systems, the governor, the brakes, to make sure they will work if needed.
So inspections aren't just looking, they're testing too.
Yes, and spotting potential problems before they become actual failures. That's the goal.
Makes sense. And beyond the mechanics, what else falls under upkeep?
Signage is important, as mentioned. Clear instructions, capacity limits, emergency numbers, who to call if it breaks down. Also, clear signs and barriers if it's out of service. Don't want anyone trying to use a broken lift.
And security sometimes plays a role.
It can, yeah. Access control systems, key cards, fobs, especially in offices or apartment buildings. Limits access for security, but also ties into managing elevator use effectively.
And this is all governed by strict rules.
Oh, yes. Very heavily regulated. In the U.S., the big one is the ASME A17.1 safety code for elevators and escalators. It sets detailed standards for design, installation, operation, inspection, testing, maintenance, everything. Plus, state-local codes often add more requirements. Following these codes is mandatory for building owners and operators.
That's good to know there's such a strong framework. Okay, let's circle back to energy. We talked about the counterweight saving a lot. Are elevators generally energy hogs or fairly efficient?
For what they do, moving hundreds or thousands of pounds vertically, they're actually quite efficient, especially traction elevators with counterweights. That balancing act makes a massive difference. Sources say elevators might only account for like 2 to 10% of a large building's total energy use.
That's less than I might have guessed.
Yeah, and certainly less energy than everyone taking the stairs. Plus, good maintenance keeps them running efficiently, preventing wasted energy.
And technology is making them even better on that front.
Definitely. There's some really cool advancements. One big one is regenerative braking.
Regenerative, like in electric cars.
Exactly the same principle. When heavy car is going down or a light car is going up, the motor actually acts like a generator. Instead of the counterweight doing all the work and maybe needing braking, the system captures that gravitational energy,
And what does it do with it?
feeds it back into the building's electrical system, or sometimes stores it in batteries. So the elevator can actually generate power during parts of its cycle. Really helps overall efficiency.
That's fantastic. What else is new or coming?
Lots of focus on passenger experience and building integration. Touchless controls using gestures or apps became big for hygiene, obviously. Destination dispatch systems are smarter. You enter your floor before getting in, and it groups people going to the same floors into the same car. Fewer stops, faster trips.
Ah, I've seen those. Less milk runs stopping at every floor.
Right. And deeper integration with building management systems. Maybe AI optimizing traffic flow in the future. It's getting smarter.
And for home elevators, any specific tech trends there?
Yeah, the sources note they've really evolved beyond just being functional. Design is huge now. Seamless integration into the home style, glass panels, sleek materials. Quieter operation is always improving. Plus, enhanced accessibility features. They're seen more as a convenience and even a luxury feature that adds value to a home.
So a far cry from just a basic lift.
Definitely more refined and integrated now.
Wow. Well, this has been a fascinating deep dive. We've covered the core mechanics, the genius of that counterweight, the different types for different jobs, the incredible safety layers starting way back with Otis, the vital role of upkeep and rules, and how tech keeps pushing things forward.
They really are these hidden pillars of modern life, aren't they?
Yeah.
You barely notice them. But our vertical world depends entirely on these complex, safe, efficient machines.
Absolutely. Hopefully for everyone listening, this gives you a totally new appreciation next time you step into an elevator. It's so much more than just a box going up and down.
It really is. And, thinking about their history, from simple ancient hoists to today's smart systems, it makes you wonder, doesn't it?
Wonder what?
Well, how will the next generation of elevators continue to shape our buildings, our cities? If vertical transport gets even faster, smarter, maybe uses magnetic levitation like some concepts explore, what new kinds of architecture or urban living does that make possible?
That's a great question. A truly vertical future, enabled by ever-evolving lifts. Something to definitely think about on your next ride.
And that wraps up today's episode of Everyday Explained. We love making sense of the world around you 5 days a week. If you enjoyed today's deep dive, consider subscribing so you don't miss out on our next discovery. I'm Chris, and I'll catch you in the next one.